Hello, everyone, and welcome to today's webinar. I'm Melissa Romero, Forensic Science Consultant and CNEN Media Group. I will be moderating today's event. This webinar is Sub-500nm simultaneous IR and Raman microscopy for microplastics and materials science research. This event is sponsored by Photothermal Spectroscopy Corporation. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of your screen or type your query into the Q&A box. If you were disconnected during the webcast, please log in again according to the instructions you received earlier. You're encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many as time permits. This webcast allows certification of participation. To receive your certificate, please click on the certificate icon below your Q&A box to download your copy after watching the webinar. Please note that CNEN does not endorse any company, products, or services that may be mentioned in the webinars. Each webinar will be archived at CNEN online after the live webcast. The presentation today is sponsored by Photothermal Spectroscopy Corporation, who have pioneered the breakthrough technique of optical photothermal infrared O-PTIR that eliminates key limitations of traditional IR spectroscopy by providing sub-micron spatial resolution for IR with transmission-like FTIR quality spectra in non-contact reflection mode. More recently, the company has developed the world's first simultaneous IR and Raman microscope and recently launched the Mirage LS with co-located O-PTIR and fluorescence microscopy. Photothermal's vision is to enable the power of sub-micron IR spectroscopy to be applied to high-value problems in industry and academia via the adoption of O-PTIR and complementary techniques. During the presentation, we will be hearing from Dr. Mustafa Kansiz and Dr. Andrew Ault. Dr. Mustafa Kansiz is Director of Product Management and Marketing at Photothermal Spectroscopy Corporation and has over 20 years of experience working with FTIR microscopy and imaging, spanning routine to research applications in both industry and academia. Throughout his time, he has worked at variant and Agilent technologies, serving in a range of technical and business developmental roles, including FTIR microscopy and imaging product manager, product specialist, R&D scientist, and European FTIR sales manager. He has a PhD from Monash University on biotechnological application of FTIR spectroscopy and multivariate statistics. Dr. Andrew Ault is Associate Professor of Chemistry in the College of Literature Sciences and the Arts at the University of Michigan. Andrew is an expert in the fields of analytical and physical chemistry with a focus on the environment. Systems of interest include aerosol, surfaces, interfaces, and engineered nanoparticles with a focus on their impacts on climate and human health. He has received a National Science Foundation Career Award from the Chemistry Division, a Sloan Research Fellowship in Chemistry in 2018, and was selected to the Top 40 Under 40 Power List by the Analytical Scientists in 2018 and 2022, and also was selected to the 40 Under 40 Recognition Program for Rising Stars in Environmental Engineering and Science by the American Academy of Environmental Engineers and Scientists in 2022. He was elected as a board member of the American Association of Aerosol Research in 2021, and he is also a member of the American Chemical Society, as well as other professional organizations. And with that being done, let's get started. I will now turn it over to Dr. Mustafa Kansiz.
Okay, thank you everybody for dialing into our webinar. I'm thrilled to be joined today with Dr. Andrew Ault. And we'll be together talking about microplastics and material science research. I'll be taking the first half of this webinar to introduce the technique, give you some background and some perspective and some context rather even, and then Andy will take over and talk about some of his new recent publications. But in typical fashion, I have a lot to say and not a great deal of time to say it in, so I'm going to jump straight into it. The outline of today will essentially consist of me discussing or introducing the issues surrounding traditional vibrational spectroscopy, so that's really FTIR and Raman, some of these emerging QCL techniques. I'll then talk about how the new technique of optical photothermal infrared, that's OPTIR, how that overcomes all of those issues, and then I'll discuss some of the configuration options available. I'll then introduce a few applications, a few examples across microplastics, some other material science, polymer examples, and then I'll hand over to Andrew for his half of this webinar. But first and foremost, let me step you through, as I see it, and I've been doing infrared spectroscopy for just over a quarter of a century here, and main issues surrounding infrared spectroscopy, and by that I mean really FTIR, and some of these emerging QCL, these direct QCL techniques, is that of limited spatial resolution. Since we are working with and using infrared radiation, we are limited by the long wavelengths. This is the laws of physics, laws of optics. So your typical spatial resolution in the information-rich areas of the spectrum is going to be really limited to that 10 to 20 micron regime. Sample preparation can be another headache, especially if you want to measure in transmission mode, and transmission mode is typically where you get the best quality spectra, and some more on that later. Some of that can be mitigated to some extent with these micro ATR crystals, but as I've said, it requires contact. Targeting can be difficult. If you're doing multiple contact points, there's the obvious contamination issues, and the samples and the crystals, you can damage the samples or you can damage the crystals, and they can be quite expensive to replace. And there's an example of indentations left along a particular sample by a micro ATR, making multiple contacts. The other issue around infrared microscopy is the sort of typical or traditional need to use liquid nitrogen cooled detectors, and these have typical hold times of 6 to 8 hours. So if you're doing long measurements, that can be a hassle, not to mention the overall handling and occupational health and safety issues. So this particular person has been reading up on the manual and has used their safety goggles and gloves. Many people don't, and you get little accidents. But one of the biggest issues, and perhaps even the most underappreciated issues, is that of this so-called dispersive scattering artifacts. Now, in the image here I have an ideal spectrum, and that really comes from this transmission measurement of a thin film of PMMA. As I said before, a thin film measured in transmission generally gives you the best quality spectra, and what I mean by good quality is a nice flat baseline, symmetric peaks. That's a pretty good looking spectrum. However, let's take the exact same material and now make it into a bead, 15 micron diameter bead, measure that in transmission. Well, now the spectrum looks decidedly different. Raised baselines with strange baseline artifacts. Even some of these peaks are now splitting and changing position. And it's now actually size dependent. So as we change the shape of these particles, the spectra change as well. And it really goes to show that spectra are very much particle shape and size and even surface topology dependent, which kind of goes against our goals here. If we're using infrared spectroscopy to identify materials, we don't want the morphology of the materials confounding the spectra, and this is often the case. On the Raman side of the vibrational equation, any Raman practitioners here, of course, would be familiar with made of autofluorescence, and a lot of biologicals, a lot of environmental samples, in fact just a lot of samples full stop, will suffer from autofluorescence, and that can be anywhere from a minor nuisance to a complete overwhelming the detector and you get nothing out of it. There are mitigations to that, but that involves using longer wavelength lasers, and that means massive sacrifice in sensitivity, and that's on top of already a limited sensitivity for Raman compared to IR. Raman can't do single frequency imaging. You must collect the full hyperspectral cube, and more on that later. If you're dealing with sensitive materials, it could be live cells, or it could be dark materials, it could be otherwise materials that are just sensitive to high levels of light. You can easily burn and damage your sample in an attempt to get better signal noise. It's a fine balance between good signal noise and too much laser power damaging your sample. And of course, there's the issue of the fact that the Raman spectra can depend heavily even on the excitation wavelength, especially if there are some visible resonances, or 785, for example, is not a good choice with glass substrates. How might this technique work? I've got a little video to take you through it. So it all starts with the microscope objective. It's a reflective Cassegrain style. Through that, we shine a pulsed infrared laser beam, and being infrared, it's fairly broad, maybe around 10 microns. At the same time, we're shining in our probe beam, the green. It's about 500 nanometers. The infrared generates thermal expansion as it's expanding, and that thermal expansion changes the way the green light is reflected or scattered back. Right, so as we're tuning our infrared laser from one wavelength to the other, we monitor the intensity of the green light reflected back. And it's from that we calculate out what is essentially a pure infrared spectrum collected in reflection mode. Arguably one of the biggest inventions and the biggest things that create excitement when we talk to people about this technique is the fact that really for the first time ever, we've truly combined infrared and Raman. So these have always been termed and thought of as complementary techniques, but that complementarity could never truly be realized, as they would always be done on different platforms with different spatial resolutions. So it was never truly complementary. But now we do IR plus Raman simultaneously, both at the sub-micron level. So that same spot, same resolution at the same time. And very quickly, I'll take you through the schematic here. So this is our infrared laser again. We shine that through our objective, this reflective Cassegrain optic that focuses the infrared down onto your sample. At the same time, as I mentioned before, we introduce the probe beam, a green beam typically, and we focus that down much more tightly, of course. Let's zoom in here. That's where that photothermal magic happens as we sweep through our wavelengths in our QCL, and that reflected green light we capture back. And we detect that at a visible detector, and I'm stressing the visible there, right, because there are no infrared detectors anymore. We simply excite the sample in the infrared, and at that point we're done with the infrared. Everything downstream from there is done in the visible domain. Of course, detectors are much more sensitive and easy to deal with in the visible. Right? And because we're using a Raman grade laser, remember there's the Raman effect is happening there all the time. There are Raman scattered photons, and whether we use them or not, it doesn't really matter. They're there. So if we want to use them, we can. We can put in a dichroic filter here, and that will then separate out only those Raman shifted photons and send them through to a Raman spectrometer, whilst the unshifted photons, Rayleigh photons, will continue on to the visible detector, thereby generating that true simultaneity when it comes to infrared and Raman measurements. Okay, so we've mentioned the complementarity, but there's also the angle of confirmatory as well. So the infrared result can confirm the Raman and vice versa. Right? People often ask me, well, how truly comparable are O-PTIR spectra to FTIR reference spectrum? So in this case or slide, I'm going to attempt to show you some reference spectra collected in FTIR off a thin film in transmission mode, so your gold standard, and I'm going to compare these to O-PTIR that have been collected with a thick block. Now this works equally well off a very thin section as well, and thin could be tens of nanometers even, so it actually works very well on thin, it works very well on thick, and these are all a few seconds collection time from half a micron spot size. So first example here is polypropylene. In red we have FTIR, in black we have O-PTIR. As you can see, that's pretty much a spot on match. Same is true for PE, PET, nylon, and polystyrene. Right, so really they are literally a one for. In fact, it's even better than FTIR in the sense that it is a more pure infrared spectrum. The only time you get an O-PTIR signal is if you have an absorbance. With FTIR, you still run the risk of having spectral artifacts, even as simple as raised baselines, from scattering of the infrared light. So non-chemically specific scattering of the infrared light. Spatial resolution is something we talk a lot about, and if you're using a microscope, you typically care about spatial resolution. There's a simple approximation for that, and that's the Rayleigh criteria. It's about 0.6 times your probe wavelength. Probe, I'm stressing that, divided by the numerical aperture of your objective. That's just a property of the objective. Now, in regular IR systems, your FTIRs, your QCL microscopes, those direct measurements, your probe is all of your wavelengths, your long to short infrared wavelengths. Hence, when you plot this plot out, it becomes a curve. Right, so in the fingerprint region for regular IR systems, you're looking up into the 10 to the low teens. Of course, we want lower numbers. And you get lower numbers, but only out in the much lesser information-rich area. But where things are interesting, your resolution is relatively coarse. But if you substitute out your long infrared wavelengths for a short visible probe of 532 nanometer, and couple that with a high NA objective, well, now your resolution theoretically is in that sort of 400 nanometer range, but excitingly, it's actually flat across the entire spectrum, much like Raman. So it actually is very, very similar to Raman in terms of its operations and characteristics. Right. So as I mentioned before, we have recently introduced the Mirage LS. That's our flagship sub-micron, sub-500 nanometer, in fact, infrared multimodal microscope, which and some of the highlights there are that it is now comes with the option for a co-located fluorescence module to be put on top, and that allows you to capture visible and fluorescence images of your sample to help guide your subsequent O-PTIR measurements. They've also introduced a new counter-propagating mode, and that comes up in the coming slides. That gives us down, certainly below 500 nanometer infrared spatial resolution, which is pretty darn exciting. And we still do, of course, simultaneous infrared and Raman, and it works great for life science application, in life science application in particular. But I'll show you some examples of where fluorescence can be useful in a microscope, in a microplastics application sense as well. And one of the most exciting things of this is this counter-propagating mode, as I mentioned. So what we mean by this, so what I showed you up until now is really where the infrared and the green come from the top. Remember, if you cast your mind back to a few slides back, where I was showing you those green and red rays coming down from the top of an objective. Well, now we've flipped that around. We now bring the infrared, we now have the option to bring the infrared from the bottom. The probe always comes from the top, but you can switch the direction of your infrared. So we call that counter-propagating mode. What that does, so that brings the infrared from the bottom. It requires a thin glass, thin infrared transparent substrate, or it could be a thin cover slip even. But the key thing there is the fact that it allows us to use high quality visible objectives for your imaging, and more on that later. Right, so some possible configurations of this is if you're working, say, dry samples, you can have a thin calcium fluoride, excite that from underneath, and then capture with a high power visible objective. You could flip it upside down and even work off thick glass slides, ideal for tissue samples, and then you can image through a thick glass slide with, say, a low mag, low NA objective. You could work with hydrated samples. You could work with fluid cells, where perhaps you have a cell in there. Again, you're exciting that from beneath with the infrared, and because the infrared doesn't have to punch through water to get through the other side, the water contributions are minimal. And that's really exciting and really almost shocking. So anyone coming from an FTIR background will know that typically we believe, or we're told, that infrared and infrared and water are completely incompatible. And that is true, except that when your infrared doesn't have to pass through water, then it's really not an issue, and that's certainly what we have here. You can also imagine the same thing on a glass cover slip without water. You could have perhaps a thin polymer film sitting underneath your glass cover slip, and you would reap the same benefits. And all of the usual tricks and tips for getting better resolution in an optical microscope are now applicable, because we are using these standard glass objectives in this counter-propagating mode. So one could use an oil immersion or a water dipping objective and get enhanced spatial resolution that way. So here's an example of a thin polymer film that's been measured on a glass cover slip upside down. And we use this as a resolution test example. So these are PMMA beads, 10 micron PMMA beads in epoxy, and we section these to a few hundred nanometers. And we've taken an image of this at 1730, so single frequency image at the carbonyl peak for your PMMA. And then if we take a cross section through there, that gives us a sense of the achievable spatial resolution. True, we're going from one polymer, the epoxy, into PMMA, and looking how sharp that interface is. And in this case, taking the 80-20 rule, we're getting around 350 nanometers. That should read, that's my typo there. So that's about 350 nanometers of resolution. And that actually marries up pretty well with what we'd expect for a 0.95 NA objective. So this is a glass compensated objective, because we are having to measure through a glass cover slip into the film beneath it that's being excited from underneath. So this is an example of counter-propagating resolution enhancement. So that's where our sub-500 nanometer claims come from. So here I'm going to go into a few applications. I won't go through all of these, of course. I'm going to leave most of these, the bulk of these, to Andrew. But as a member of this company, as a person involved in marketing and business development, nothing gives me more joy to see publications on the rise. Really, there's no better validation of the uptake and the worth and value of this technique than scientists, academics publishing, and publishing en masse as well. And in particular, in 2022 was a bumper year, and that will be a exponential rise. And even in the first month of this year, we've seen several papers come out already. So that trend will continue, and that, for me, as I said, is quite exciting. Given our microplastics theme, I can't help but perhaps highlight, and dare I say even show off, our perhaps strongest paper, and this was published in Nature Nanotechnology with an impact factor of 39. This was a fascinating paper that looked into the effects of steam disinfection on silicone baby teats or baby nipples. And this was examined, this was a Chinese group, this was examined with optical photothermal infrared, and they were able to look at the pitting and the change in chemistry and the flaking off of very, very small particles, even down to sort of 600 nanometers were claimed. And that was quite a surprise, as people thought the steam disinfection process, that the teats themselves were quite robust against steam disinfection. Well, it turns out they're not. They do shed a lot of silicone microplastics, and there's changes in chemistries, and there's other contaminants that leach out as well. So that was a great paper. Maybe not so great for the babies, though. Another recent and exciting microplastics paper came out from the Christoph Kraft group in Jena in Germany, and he used simultaneous infrared and Raman, but really novelly combined hit quality indexes in a two-dimensional format. So each spectrum was searched against a reference database, and their hits were plotted in one direction for Raman and O-PTIR or infrared in the other direction. And that was able to help them overcome a few of these issues. And some of those issues are listed here. So with environmental microplastics, they'll often have some coating on them, some biofouling, some bacterial coating maybe, which often leads to severe fluorescence, and that really can interfere with the Raman channel. Pigmented microplastics can also have issues with Raman. If it's not burning, then it's probably some resonance enhancement, leading to the pigment of the dye itself being dominant, with little to no polymer contributions into the Raman spectrum. But if you flip that around, if you have a carbon-loaded microplastics, for example, tire wear, so road runoff, or even just pure carbon particle soot, they have really strong and characteristic Raman signals, but the infrared has very little characteristic features that you can pull out from that. So that's, again, comes back to the complementarity of infrared and Raman, and why those two working together in unison, in synergy, offers so much value. And in this case, so this is a screenshot from this paper. So if you look at this cluster of particles, so these were polystyrene beads that were dyed red or dyed blue, and they receive fairly high infrared scores, OPTIR scores, but if you go across here, their Raman scores are quite poor. And that comes back to the second point with that pigmented particles, pigmented fibers, particles, or really anything pigmented in the Raman can be a real challenge. If it's not burning, then it's resonance and enhancement that swamps the underlying polymer signature. Some real-world examples of microplastics on gold-coated polycarbonate filters, infrared spectrum, simultaneous Raman spectrum. If you search that against a library database, and we've got exports directly from our software into the Wiley know-it-all databases. This is a screen capture from their software, so it's rather a seamless process, and you can see the infrared and Raman are a great match. So that's clearly in high confidence PET. This is a polyethylene match. This was a blue fiber, so in this case we've only got infrared. The Raman was too fluorescent, and even if you search that against a database, you can see that's actually a composite of cellulose and the blue dye. So that the sensitivity is to that level, and the spectral quality more so is to that level. So if anyone ever has tried to measure a 10 micron fiber in reflection mode with an infrared, you'll know that you get essentially noise back from that. Right, but it's not just about microparticles. The system works incredibly well for particles that are hundreds of micron in size. Right, so the challenge with particles that are hundreds of microns in size for a traditional IR would be that you would have saturation effects. These peaks would be cut off, making their interpretation, making their searching very difficult. But with O-PTIR, whether it's hundreds of microns or millimeters, really doesn't really matter, or whether you're looking at sub-500 nm particles, the spectra look like spectra that are interpretable and searchable. All right. This is a couple of examples of how fluorescence might be coupled to make the microplastics workflow more efficient. All right, so those of you from the microplastics background might be familiar with the use of Nile red. Nile red is a lipophilic dye or stain that generally and preferentially attaches to polymeric samples and not other inorganics, and therefore under a fluorescent microscope one could count and visualize the polymers. But of course with a fluorescence microscope you don't know the chemistry, you just know that the dye stuck to something that is likely to be polymeric. So on the right hand side, excuse the unlabeled nature, but that's a fluorescence image, that's a visible image. So you can see that some particles have lit up. You can see this dark particle here is lit up in the fluorescence. This small particle over here has lit up there as well. And without the fluorescence, all of these particles could well be considered polymeric in nature, but they clearly weren't. Only those that have taken up the lipophilic Nile red dye are polymeric. And when we go in there and when we're guided by the fluorescence image, we collect pure polymer spectra that are easily recognizable. Most of you probably won't even have to search that in the library. That's PET, sorry, that's PE, and that's PET underneath it. So this really improves the efficiency by only allowing you to measure the particles of interest. And that reduces the burden on upstream cleanup. Because there's a huge science when it comes to microplastics about how do you treat and clean up the microplastics in order for you to most easily and efficiently measure them. Well, if you could do less work upstream, it helps the overall workflow be a lot more efficient. For those of you who are into heating your sample, cooling your sample, and just looking to see what happens while we maybe melt and heat and maybe pass some gases over it, those of you perhaps in a more catalysis sphere, we do offer heating and cooling stages, and these can be Peltier controlled from -20 to 120, or from ambient up to 250 with a resistive model, and that fits under the microscope, and the working distance of this objective allows you to reach the heating element through the top window, and that can be controlled with an external controller, and just some spectra. So that's that similar PHA material, the biodegradable polymer, the bioplastic, and we've gone from 40 to 160 degrees in reflection mode. These are raw spectra, right? So we go from the top here, which is at around 40 degrees, and as we go up in temperature, the peaks change. We go from crystalline phase to a purely amorphous phase, and we see exactly the same information, well, in a more complementary sense in the Raman. So you can then combine these data sets to do 2D correlation spectroscopy and work out mechanisms of how things change. It's the mind boggles at how much information is there and how you can now use all of these new emerging mathematical tools to extract out. Because the more data you have, the more information you can extract out of it. And that brings me to my summary slide. With our flagship product, the Mirage LS, we've taken infrared microscopy beyond the traditional and accepted limits. That's a term I sometimes use to refer back to what is hopefully moving to be the more old-fashioned FTIR, QCL sort of microscopes. It's now sub-micron. We operate in reflection mode primarily, so it's non-contact, non-destructive, and you get transmission-like spectra. With the LS, we've now introduced fluorescence as an option, and that helps guide your O-PTIR measurements if there's perhaps not enough contrast in the visible. And that's sometimes the case. You may not know where to measure based purely on the bright field visible image, and that's where having some external dye or even just relying on the autofluorescence can help guide your measurement. The new counterpropagating mode takes us from sub-micron now to sub-500 nanometers. And maybe my favorite still is, of course, the IR and Raman, same spot, same time, same resolution. And with that, I'm going to hand over to Andy. Thank you.
Hi, everyone. My name is Andrew Ault, and I'm an associate professor at the University of Michigan. And today I'm going to tell you a bit about some of our research, which has utilized the optical photothermal infrared spectroscopy measurements that you've just heard about from Mustafa. And a little bit of background about what my group focuses on. We're very interested in the environmental chemistry space, and in particular, we study individual particles that are in the atmosphere or other places within the environment. And this can include everything from microplastics to air pollution or haze, what we call secondary organic aerosol particles, all the way to organic material that gets emitted from oceans when waves break. But the overarching theme of what we do is that we use individual particle measurements like the O-PTIR, Raman spectroscopy, electron microscopy, to try to understand at a particle by particle level what these microscopic sized entities in the atmosphere are made of and what their properties are. And so before I get into this too deeply, I just want to point out that aerosols are incredibly complex and they have global impacts. A typical aerosol is a mixture of thousands of different species within either small droplets or solid particles. They can be gooey tar balls, they can be glassy marbles, they can be liquid droplets. It's really a wide range. And within just one of these, micron-ish sized particles, all the way down to a few nanometers, you can have thousands of species, as well as very large pH ranges, and as I mentioned, different phases. So why do we care about these particles? If you take a deep breath with me right now and go, you've breathed in about 1 million particles during that breath. And so we are constantly breathing particles. And for that reason, the impacts of breathing in air pollution have been associated with somewhere on the order of roughly 7 to 8% of global deaths annually from all sort of illnesses related to cardiovascular disease, respiratory disease, even heart attacks and strokes. So aerosols can have huge impacts on health. They also can have huge impacts on health, as we've all learned in recent years, through transmitting infectious diseases. And we know that aerosols can impact our climate. In fact, are one of the greatest uncertainties when it comes to the warming or cooling of the planet, because they can both scatter and absorb light from the sun by themselves, or they can change the properties of clouds, which impacts both how much solar radiation comes through the Earth's atmosphere or how much Earth terrestrial radiation from the Earth acting as a black body can get released out from our atmosphere. And so the most important aspect of this is that every single one of these impacts that I've discussed relates to the fact that a particle acts on an individual basis, whether it's taking up water to be able to form a cloud droplet. That's an individual particle process. And thus we need to understand at a particle by particle level what they're made of. And the same is true for health, visibility, and other effects. So I'm just going to tell you 3 little examples of the kind of research that we do in my group today, as well as how we use microspectroscopy techniques to leverage those to try to learn more about them. So first, I'll tell you a little bit about a recent paper we had in ACS measurement gold from the American Chemical Society, where we looked at sea spray aerosol composition, both inorganic covalently bonded molecules, as well as the organic species present. We looked at urban air pollution, including things like haze. And we looked also more recently at microplastics, which we've been really excited to team up with Photothermal to try to utilize some of their methods and improve the techniques that we have available in our laboratory. So when we approach any of these problems that we're interested in, be they air pollution, haze, whether they be naturally emitted particles or whether they be microplastics, we take a sort of 1 foot in the lab, 1 foot in the field approach to it. And we think that this really helps us keep us grounded, but also tackles the complexity of the real world. And so we start in the lab where we use model systems, synthesized molecules, very simplistic, but well-characterized samples that we can understand, connect with things like density functional theory, other sorts of computational or experimental methods that are really going to give us an idea as to what's going on with these particles. We then can do flow tube chamber studies. I'll talk a little bit about what we call a marine aerosol reference take, where we can make particles in the lab from water in a representative way as to how it happens over the oceans or Great Lakes. And then lastly, we like to get a little dirty and get out in the field and actually collect particles. Here you're seeing an image with the sunset there from the University of Michigan's biological station in northern Michigan, where they have a 100-foot tower that you can sample from the top of and collect particles to understand what's happening in a sort of remote area. And so with all of these, we have a range of tools that we bring to bear on the problem. And so typically our approach is that we collect particles onto a substrate, and that substrate can be anything from a microscope slide to a sheet of aluminum to a silicon wafer, or even fancier things like gold-coated silicon wafers, SIR substrates, and so on. But for all of these, we collect a particle onto a surface where we can then bring it back to the lab to look at it with one of our instruments. And the first instrument I got into when I was starting here at Michigan was we had a Raman microscope. So that Raman microspectrometer was incredibly useful, but there were some limitations. I'll mention some of those that got us excited to try optical photothermal infrared later. We also did a lot of electron microscopy, where we would not only look at how the particles, sort of what their imaging would look like with the electron images, but also try to understand their elemental composition based on the X-ray that are emitted from electron beam microscopy. We also did atomic force microscopy, but that was a little bit limited in that it didn't have any chemical information. And as chemists, we want to understand what things are made of. But the things that we've really gotten into and are excited about are photothermal infrared spectroscopy, both coupled with atomic force microscopy, and more recently with optical photothermal infrared spectroscopy, which has really become a workhorse in our lab in recent years. And so when we started with atomic force microscopy coupled with photothermal infrared, we published the first paper applying this to atmospheric particles with Amy Bondi, my first grad student here. You can see her in the upper right corner. And she was able to look at particles on a silicon wafer, which is the image you're seeing here in the middle. And she was able to collect infrared spectra that had, the peaks in the same positions over here on the right side for ammonium and sulfate, for an ammonium sulfate aerosol particle that we collected on the substrate. But there were a couple of drawbacks. One of the biggest was the fact that when we were working with AFM, we often work with kind of gooey or sticky molecules. And so this was really challenging to do with the tips. And so contactless was a really, when we heard there was a contactless option for photothermal infrared, we were really excited about that. And so we published one of the first papers, the first one on atmospheric aerosols, and one of the earlier papers on optical photothermal infrared coupled with Raman spectroscopy. And this was for the sub-micron analysis of sub-micron aerosol particles that we collected, both from the field as well as in the lab. And this was led by Nicole Olson, another graduate student of mine. You can see in the upper right corner there. And here, the difference is that we're using the green 532 laser, which is what's going to give us our spatial resolution, as Mustafa explained, similar to what we get with our Raman microscope. And we're going to watch the change in the scattering of that signal, and that's going to tell us about the photothermal infrared response. But at the same time, we're also getting, and you can see the response equation down here at the bottom, which is related to the absorption cross-section, a couple of heat-related terms, conductivity and capacity, as well as the change in refractive index as it increases in temperature from absorbing the IR. But the other side of this is that we get really nice spectra. So here you can see the ammonium and sulfate, the ammonium band and the sulfate asymmetric stretch, which is shown for a particle that we generated in the lab that we knew what it was made of. What's really nice is that when we do this, we at the same time are still inelastically scattering Raman photons. And so we can still get Raman shifted spectra that we can look at collected simultaneously with the IR spectra. And so here you can see the Raman symmetric stretch of the sulfate group at the same time as the asymmetric in the IR, where that has a greater dipole moment, is more active, the polarizability is more active for the symmetric stretch of the sulfate group. And so with these, we were getting them both at the same time. And in a lot of the work that we do, and it's true, I'm sure, in many other fields like materials and life sciences, being able to identify multiple modes, both based on their dipole and polarizability, really opens doors in terms of having greater confidence in our spectral assignments. And so the first thing we did is we said, okay, what are the substrates we can take out into the field if we want to make a measurement with this? And so we tried our usual suspects that we have used over the years: silicon chips that we break into small pieces, quartz, germanium, aluminum foil, and silver foil. And as you can see on the left side here, and the figures in higher resolution in the article that's referenced at the bottom of the slide, and you can see that we had all the peaks that we would expect where we would expect them. The ammonium bend, for example, is very IR active, but not Raman active. So it's in the IR, but not the Raman. The sulfate modes are at the two positions I talked about on the last slide. And things lined up quite well with what we were looking for. And it turned out that we've mostly actually been using silicon wafers for our more recent analysis. They ended up working quite well. So then we said, all right, let's kind of, let's test what this baby can do, and let's, put a couple of different chemical compounds that are proxies for the types of things we might see in aerosols or other environmental samples. And so we looked at ammonium nitrate, sodium acetate, sucrose, sodium dodecyl sulfate, and ammonium oxalate that you can see here. And in both cases, the Raman and IR matched up very nicely with spectral libraries that we had on the instrument. So that kind of established that we could, look at this with controlled samples in the lab, but what happens when we start working with more complex particles? So as part of an NSF-funded project that actually is with collaborators, Patty Matrai at Bigelow Ocean Sciences Lab, Carrie Pratt here at Michigan, and Amanda Granis at Villanova, we collected particles with a marine aerosol reference tank using fresh seawater from the Gulf of Maine that you can see in the picture here in the lower right. And what we were looking at is that we wanted to understand for this coastal environment where you have, lakes and rivers that are freshwater, feeding into this bay, we wanted to understand what the organic composition of aerosol emitted from that would be. And so these marine aerosol reference tanks that I'm showing in the lower left here have been validated by folks at Scripps Institution of Oceanography and are commercially sold, very well characterized. And we said, all right, let's collect some of these particles and look at these with our Raman, but also with our new optical photothermal infrared method. And so we started with electron microscopy. This has kind of been an old workhorse for us. And lo and behold, we saw that there were sodium chloride, not that shocking, as well as some carbon in there. But as anyone that's done EDX knows, you're not going to get any organic information out of the carbon peak in an EDX spectrum. And so we wanted to understand, when we just said, that we had sea spray aerosol with organic carbon, we wanted to know what was in that organic carbon. And so what we did is that we looked at a number of our different experiments here, and you can see that we had these here are Raman spectra. You can see that we have some really nice features in here. We have, all across the CH stretching region, you've got very sharp peaks across these different experiments, and they're not always in the same positions, which is always, interesting and exciting. And so we were able to start to understand what these were consisting of. And these are on the left here are all averages of quite a number of spectra, but I wanted to show you on the right here some of the different individual spectra for the particles that are in the upper left here. And one of the things I wanted to make a point of is that you actually get quite a bit of good reproducibility. There's the occasional outlier, but a lot of these peaks are very reproducible. But we do have the occasional problem of a particle that has a fluorescent background, or something that is going to really be kind of a challenge. You can see that particularly here, this last experiment, we added some biological material to the sample, and you can see that we really started to have a large background issue. So this Raman work was building on some work we had done as part of a PNAS paper earlier this year, led by Rachel Kerpis, who's now at EPA, where we were looking at organic and inorganic components within the Arctic, within aerosols collected at Kayavik or Barrow on the north coast of Alaska, as well as some work here using Raman to try to break down the different categories of organic species that we were seeing within the organic component of these sea spray aerosol. And so you can see categories such as saccharides, amino acids, short-chain fatty acids, long-chain fatty acids for these particles, where you can see in the electron micrograph over here on the right, a salt particle and then organic content kind of looping around it. That had dried on that substrate. And this actually built on some really nice work by Rich Cochran and Vicki Grassian at the University of California, San Diego, the chi-squared analysis we did for these different categories of organic species. And so here you can see some standards that we had run, including saccharides, looking at lipopolysaccharides, different carbohydrates, different fatty acids. And when we ended up categorizing the different spectra that we had, it turned out quite nicely that we were able to say for each experiment for two different size ranges of particle are super micron, so 1 to 1.8 micrometers in aerodynamic diameter, or sub-micron here, 320 to 560 nanometers. And so we were able to see differences. Some experiments had them, they were more stark, others they were more subtle. But we were excited to see what the O-PTIR could do. And so we did a similar sort of analysis there. And when we were doing this, you can see here again, similar spectra averaged across these different experiments. But what was really exciting is that when we started to look at the reproducibility of these spectra, on the whole, considering each particle is its own individual entity and is going to have slightly different composition, overall, the spectra were really quite reproducible. And so now having both the Raman that we've had years of experience with, as well as this new optical photothermal these optical photothermal infrared spectra, we're able to really get a great feel for these different samples. So this is just one kind of flavor of the way that we use Raman and optical photothermal infrared to analyze our samples. But one of the other science questions that we look at is trying to understand haze or air pollution in urban areas, particularly organic aerosol. If you've ever, driven through a downtown area in the middle of summer, it's kind of got a white haze looking thing going on. A lot of that is organic aerosol that has formed, not coming out of a tailpipe, but after reactions that occurred in the atmosphere. And so the way this happens is you get some sort of a gas emitted to the atmosphere. It could be anthropogenic, or it could be from plants and trees. But once that gas gets up there, it's going to undergo some different reactions here. And in the case of this isoprene here, it'll actually form quite a lot of this epoxide called IEPOX, which was discovered by Jason Surratt, who's at UNC, John Seinfeld, and Paul Weinberg at Caltech. And so what they saw was that the epoxide is a large component of the oxidation products of this isoprene. And this has a very low vapor pressure. And so what happens is that if there are particles emitted, from cars, trucks, industry, and this molecule here, which has a very low vapor pressure compared to the initially emitted isoprene, this gas is going to say, oh, there's a particle. I'm going to go in there, and when I do, I'm going to make that particle grow. And that's how you get a lot of these large particles scattering light and getting breathed in by folks in urban areas. The challenge has been always identifying the organic components within this. And so if you go back and look at some work from the early 2000s, back when I started grad school, you can see that organic components were known to be 30 or so percent, 35% of the overall air pollution that was in the particulate matter that was in the atmosphere. But if you tried to break that down, a large fraction of that fell into categories where we couldn't determine what the chemical composition was. It was either non-extractable, non-elutable, unresolved, unidentified, and then this tiny little box down here is where it was identified. And so we knew some of these were carboxylic acids, but a lot of it we didn't. And so in more recent years, we've been able to identify that we still have roughly, this is for Beijing just about a decade ago, we were able to say, we have similar fractions of these different types of particles, but if we look at the how much of this is coming from these atmospheric reactions, like you're seeing over here on the left side, it's over 51%, either for organic molecules like we're seeing, or for inorganic components like sulfate or nitrate mixed with ammonium. And so because of these secondary things, there's a particular pathway that we study, which is that IEPOX. It goes in and it forms after protonating the epoxide, this sulfate group will undergo nucleophilic attack, pop open the epoxide, and leave us with an organosulfate and 3 OH groups. Or we can have it water attack it and give us a tetrol. But in either case, we form these molecules, and we know that they can be 15 to 20% of organic material in cities like Atlanta during the summer, but we don't know a lot about how viscous they are. Do they form core shell morphologies? Do they eventually break down and have that sulfate group fall back off? These are all questions that my group and our collaboration with Jason Surratt down at UNC that we focus on. So how does this tie into OPTIR? Well, one of the things that my collaborator is able to do is that he synthesizes pure versions of these methyl tetrol sulfates that I just mentioned on the last slide. And so those organosulfates, just have been recently synthesized in the last 5 years. And so we wanted to, really at a fundamental level, understand what they were made of. So we did density functional theory. You can see here on the right side, the optimized structures that we got for the organosulfates, both when it is in a deprotonated or anionic form here, as well as with an protonated and neutral form. And actually the PK is a really interesting question I don't have time to talk about today, but that we've been exploring for these. But what we were able to do is to collect Raman spectra, using as well as calculate where the Raman peaks should be for both the protonated and unprotonated forms, based on that density functional theory and vibrational mode analysis. But what about the IR? And so here, we've known the Raman peak for these organosulfates was roughly in the 1075 wave number range, but we didn't really know where the IR was, and that's where we were excited. And so we took some of our pure sample and looked at it with your workhorse ATR, FTIR, but it takes a bit of material, and it's not actually what's in the aerosol phase, right? It's just what we're getting from the synthetic products. And so what we also did is we compared what we got with that ATR, FTIR with aerosolized particles that we looked at with both the optical photothermal infrared as well as the AFM-PTIR that I mentioned before. And the blue trace here for the optical photothermal, and this was, I should say, published in Fankhauser et al. Last year in Journal of Physical Chemistry A. You can see really nice agreement between these different peaks here for the two sets of samples. So that was really exciting for us. And the last thing we've been working on more recently is trying to understand microplastics. Microplastics, are really readily accessible by Raman and IR. One of the challenges, as with all things with Raman, is that if you have a fluorescence, it can be a real challenge. And a lot of atmospheric molecules have a tendency to fluoresce. And so that's part of why we've been chasing the OPTIR to try to see if that can help us get around that issue. And so microplastics in the atmosphere have actually been getting a lot of interest in the last couple of years. This nice paper from PNAS a couple of years ago shows some of the different hypothetical sources, and there's been numerous identified since then that also contribute to the atmospheric limit of the plastic cycle. But we're very measurement constrained. So over on the right side here, you can see, there's just been a few measurements, as of this paper about 2 years ago, in terms of where samples have been collected. And that was actually primarily from deposition, not necessarily atmospheric sampling. So I'm part of a project here at the University of Michigan that's led by Ann McNeil, a polymer chemist and organic professor in the department, myself, as well as some folks here, Paul Zimmerman, physical chemist, and Boosh Dewari, a statistician, and Allison Steiner, who is an atmospheric modeler up in our climate and space sciences and engineering department. We've all come together to try to understand how widely distributed are microplastics in the atmosphere. And we're using a bunch of aerosol sampling techniques. I won't go into the details on those today, but the goal is that we're going to sample at a large number of high schools across Michigan, look for microplastics using OPTIR and Raman together, and then we're going to try to make a prediction as to how these are distributed across, using Allison's atmospheric models, how they're distributed across the state. And there's different sources in different regions, so it's not necessarily going to be a straightforward answer, but that's actually, I think, particularly interesting. One of the most exciting things about science is when you don't necessarily know for sure what you're going to see. And we're just in the pilot phase of this right now, so really spinning this up. But one of the things we had to identify was what method are we going to use to look at these microplastics? And then for anything to stay in the atmosphere for an appreciable amount of time, it's got to be smaller than about 10 micrometers in diameter, and really to stay up for more than a couple of hours, and it should be smaller than 2 or 3 micrometers. And so one of the challenges we ran into, and we sent samples of ours to a couple of different, sort of traditional IR microscope folks to look at, and getting below 20 nanometers, micrometers, 10 micrometers was pretty challenging, and certainly below 5 for an environmental sample. And so when we turned to photothermal and said, hey, we're really interested in this. Is this something you think your instrument can handle? We got a sample together the same way we prepared them when we sent to the couple of other folks. And we ended up getting some data back that was really exciting. And so here you can see, so we put 3 different types of plastic particles over here on this it's called silicon wafer. You can see over on the right side here, this is using the QCL that has the CH stretching region, which is going to be really critical for our analysis, where you're able to identify, these different polymers, the red, the blue, and the green. And the green are actually atmospheric particles that aren't the microplastics. And then you can see down here on the bottom, this is the Raman spectrum for those same particles as we have IR spectra up top. And so, these are really sharp, nice looking spectra. And, we're working both with our statistical colleagues as well as, using things like the Wiley Know-It-All software to try to match these now and get a good understanding. And so we also played around with some of the modes such as transmission to see if we could get some good signal from that. We actually got pretty good signal, as well as we did some mapping to try to see if we could isolate the different modes. And so you'll see 2 different modes mapped here, 1600 as well as 1730, which were present in the previous spectra, and they worked out quite well. So part of what we've started with is just looking at the different sources of microplastics. And excuse me, we're doing that by putting microplastics into our seawater aerosol generation tank. And we've started just with the Raman for looking at this, but you can see here that we are able to identify microplastics out of a whole sea of other particles that are just primarily salts coming out of the seawater from our marine aerosol reference tank. And these showed up quite nicely. And so what we're excited about, we haven't upgraded to be able to do the CH laser in our lab yet, although that's happening in a few weeks. And when that does, we're really excited to compare the CH stretching regions for the Raman and the IR and start optimizing our matching, particularly accounting for things like weathering.
Thank you so much to Dr. Mustafa Kansiz and Dr. Andrew Ault for that excellent presentation. I love instrumentation, so this was fascinating for me also. And now we're going to open it up to questions. Our first question is for Andy. Does your group still use your traditional Raman? And if so, what advantages are there to using a traditional Raman spectrometer instead of the OPTIR Raman?
So we do still use our traditional Raman somewhat. I would say that if we have the choice, we typically like to use the FTIR just because of that complementary information. The only real benefit we get is that we get a slightly higher numerical aperture on our traditional Raman, just because that lens, we don't have to worry about collimating both the IR and visible light through it like you do with the gaseous grain. But it's we don't get a ton of extra benefit from that. And I'd say the other thing is we do some computer-controlled analysis, which is something I know Photothermal is working on. And once that's available, I have a feeling we'll be using the OPTIR plus Raman probably more.
More often, okay. This question is also for you, Andy. Why use OPTIR plus Raman when SEM-EDX can chemically analyze smaller particles? Question.
Yeah, so the biggest thing that comes down to is that we want to be able to identify. We want to be able to match these spectra to known, we're looking at microplastics, for example, to known polymers. And the EDX is only going to give us that, tell us that there's carbon present, but not what it is. It wouldn't tell us, soot from certain, secondary organic things from microplastics, whereas we can get that information with the Raman and the IR. And having both, a lot of the times the peaks, will be not entirely clear if you're just using one of the two, but if you have both, then it ends up being really, really powerful. So getting that vibrational spectra, that functional group information is really key.
Okay, excellent. Andy, so why is it important to analyze particles approximately 1 micron that are too small for conventional IR microscopes?
This is actually a really key thing for a lot of environmental analysis, simply because for things in the atmosphere, if it's 1 micron, it'll stay in the air, for days, even weeks. Whereas if it's, much larger, it won't stay up for very long. So when we're trying to look at atmospheric microplastics or just particles in general, we want to look at the ones that stay up in the air the longest and then have the largest impacts on whether we breathe them in or they, impact the properties of clouds. So being able to get smaller than, 10, 20 microns, as with a lot of other IR microscopes, really does make a difference in terms of whether we can look at relevant samples.
Okay, and that's about all the time that we have today. Thank you again, Dr. Mustafa Kansiz and Dr. Andrew Ault, for this excellent presentation. Again, I found it very wonderful. I just want to remind the audience that all of the questions that we did get, if we didn't get to yours, they are logged, and they will be answered directly through email after the webinar. So thank you, participants, for being a great audience. Be sure to check CNN or CNN Online for information on the next edition of CNN webinars. Thank you to On24 for the technology and production services, and thank you to Photothermal Spectroscopy Corporation for the sponsorship that made this interactive webcast possible. For CNN webinars, I'm Melissa O'Meara. Goodbye.